Some people think that in the future the technology will exist for humans to be made to order. Parents may be able to decide whether they want a child with blonde hair or brown, green eyes or blue, one full of caution, or a risk taker. The possibility of engineering human beings likely would spark a lot of controversy. But not so long ago, biologists were still trying to figure out how traits were passed from parent to child. In the middle of the 19th century, an Austrian monk named Gregor Mendel was the first to show that discrete factors were passed from parent to offspring. These factors are now known to be forms of genes. Mendel's pioneering experiments involved the familiar pea. He crossed a purebred yellow pea, which had a pair of factors we'll call YY, with a purebred green pea, GG. Mendel hypothesized that the pea offspring would get one factor from each parent. We can chart all the possible combinations on one kind of tree diagram. One of the Ys can pair with either G. The other Y can also pair with either of the G factors. So altogether, there are 4 possibilities. This set of all possibilities is called the sample space. Considering it can help us determine the probability of any particular outcome. Probability can be expressed as a fraction. The denominator is the total number of possible outcomes. The numerator represents the number of ways the event of interest can happen. So back to Mendel's peas. What's the probability the first pea generation will be YY? The denominator, the total number of possible outcomes, is 4. How many YYs are there in the first generation in the tree diagram? 0. So the probability is 0 out of 4, 0/4, or 0, meaning it cannot happen. What about YGs? The probability of that is 4 out of 4, or 1, meaning it is certain to happen. The probability of any event is always between 0 and 1, from impossible to certain. Now let's look at a couple of other ways we can use ideas about probability to solve problems. They can travel up to 43 miles an hour and have a unique means of getting around. When they need to get somewhere fast, it's almost certain that kangaroos will use their large, powerful hind legs to hop there. Not everything about kangaroo life is that predictable. For a pregnant kangaroo, the gender of its baby, called a joey, is by nature a surprise. That's because the joey is just as likely to be male as it is to be female. It's the equivalent of a coin toss. There are 2 possible outcomes. The coin will land heads up or tails up. The probability you'll get heads can be expressed as a fraction. The denominator is the total number of possibilities, 2. The numerator is the number of those possibilities that are heads, 1. So the probability of heads is 1 out of 2, or 50%. The probability of getting tails is also 50%. Likewise for the gender of a joey. There are 2 possible outcomes, male or female. Like all mammals, kangaroos have 2 sex chromosomes. The female has 2 X chromosomes. The male has 1 X and 1 Y. Each offspring will inherit 1 sex chromosome from its mother and 1 from its father. We can make a table showing all the possible combinations. This set of all possibilities is called the sample space. It can help us identify the probability of any one outcome. Let's start by pairing the female's first X with the male's X. That's one possibility. And then pair that first X with the male's Y. A second possibility. We can also pair the female's second X with the male's X, and the female's second X with the male's Y. Two more possibilities. The table makes it easy to see that there are 4 possible outcomes. Of the 4, 2 are XX, female, and 2 are XY, male. We can express the probabilities as fractions. 2/4, or 1/2, or as a percent, 50%. The probability the baby kangaroo in the mother kangaroo's pouch is female is 50%. The probability it's a male kangaroo is the same. Call it. There are only 2 possible outcomes, heads or tails. The probability you'll get heads is 1 out of 2, or 50%. The same is true of tails. But what if we're tossing something with more possibilities, like a number cube with 6 sides? There are 6 equally likely outcomes. This set of all possible outcomes, 6 total, is called the sample space for the cube. Add another cube, and the number of possible combined outcomes is much greater. How much greater? Well, there are 6 possible outcomes on the first number cube, the numbers 1 through 6. And the same is true of the second number cube. A 1 on the first cube could occur with any of the 6 numbers on the second cube. The same is true for any of the other numbers on the first cube. So there are 6 times 6 possible combinations for the numbers on the 2 cubes. 36. But what's the possibility of getting a 4? Well, we could get it in various ways. A combination of a 1 and a 3, a 2 and a 2, and a 3 and a 1. That's 3 different ways out of 36 total possibilities. 3 out of 36, or about 8%. The greatest probability? Getting a 7. There's a 6 in 36 chance, about 17%. That's because you can get the number 7 with more combination rolls of the number cubes. See? The lowest probability, the least likely outcome? Getting a 2 or a 12. Just 1 shot in 36 of doing either of those. About 3% each. Toss a coin. There are only 2 possible outcomes, heads or tails. The probability you'll get heads is 1 out of 2, or 50%. The same is true of tails. Now let's toss 2 coins. What's the probability both will land heads up? To figure that out, we can make a tree diagram of all the possible outcomes. Coin 1 could land on heads, and so could coin 2. Or coin 1 is heads and coin 2 tails. What if coin 1 lands on tails? Coin 2 might come up heads or tails. We can see there are 4 possible outcomes. This is known as our sample space. Of the 4, how many are heads? Just 1. The combined probability that 2 coins will land heads up is 1 in 4. We can show the same information in a table with the possibilities for coin 1 in rows and for coin 2 in columns. Now let's figure out the combined probability both coins will be heads 2 times in a row. We know the combined probability of getting 2 heads on the first toss is 1 in 4. Let's show this with the 4 possible outcomes along one side of a new table for the rows. For the second toss, the combined probability both coins will land heads up is the same, 1 out of 4. Let's put the 4 possible outcomes of this toss at the top of the table, labeling the columns. To find the combined probability both coins will be heads on both tosses, we multiply the probability of 2 heads on the first toss by the probability of 2 heads on the second toss. 1 out of 4 times 1 out of 4 equals 1 out of 16, 1/16. The combined probability both coins will land heads up 5 times in a row is 1/4 times 1/4 times 1/4 times 1/4 times 1/4, or 1 out of 1,024 trials. Not very likely.